Please pause the video and try this problem. Now let's discuss the problem. Remember that if you find that these video explanations move too slowly, you can simply try the problems in the problems document, study the solutions in the solutions documents, and if necessary, use the table of contents at the bottom of each video to skip to the particular parts of the videos that cover the parts of the solutions that are giving you difficulty. Here are some keyboard shortcuts which you may find useful while you're watching the videos. Here is a summary of the solution to the problem. And now let's discuss the solution step by step. The problem mentions the concepts of mass, acceleration, and friction, which is a force. And all of those are concepts which we can substitute into the Newton's second law equations. So we're going to apply the Newton's second law problem-solving framework for this problem. The problem asks us for the acceleration of the mass. Now, acceleration is a vector, so I'm going to choose to interpret this question as asking us for the direction of the acceleration vector and the magnitude of the acceleration vector. The problem says that the mass slides down a hill, which indicates that the object is moving parallel to and down the hill. So I'll draw the velocity vector pointing parallel to and down the hill to indicate the object's direction of motion. Kilograms are SI units, so we've checked that the given units are SI units. Now let's work on the free body diagram. The problem mentions the mass of an object which is referred to as the mass. And that's a clue that our free body diagram should focus on that object which is referred to as the mass. First, we identify the object's weight. And then we ask, what is touching this mass? Well, the mass is being touched by the hill. The hill forms an inclined plane, which is the type of thing that we treat as a surface. A surface can exert both a normal force and a frictional force. The mass is sliding, so the hill will exert a kinetic friction force on the mass. Are there any other forces being exerted on the mass? Well, ask, is there anything else that is touching the mass besides the hill? No, nothing else is touching this mass, so there are no other forces to include in the free body diagram. The direction of the weight force is always straight down. Notice that the fact that the mass is on an incline has no effect on the direction of the weight force. The direction of the normal force exerted by a surface on an object is perpendicular to and away from the surface that is touching the object. So, the direction of the normal force exerted by the surface of the hill on the mass is perpendicular to and away from the surface of the hill, like so. The direction of the kinetic friction force exerted by a surface on an object is parallel to the surface and opposite to the direction that the object is sliding. So, the direction of the kinetic friction force exerted by the surface of the hill on the mass is parallel to the surface of the hill and opposite to the direction that the mass is sliding. In this problem, the mass is sliding down the hill, so the kinetic friction force points parallel to and up the hill, like so. Friction opposes sliding. Remember, the normal force will always be perpendicular to the surface, and the friction force will always be parallel to the surface. Next, let's work on the force table. In the first row of the force table, we want to represent the magnitudes of the overall force vectors. On this problem, we were not given a value for any of the forces. There is a special formula for finding the magnitude of the weight. We use this special formula to determine that the magnitude of the weight is 98 newtons. And we use this special formula to represent the magnitude of the kinetic friction force. Now, there is no special formula for the magnitude of the normal force, so we simply represent the magnitude of the normal force by the symbol little n, written without an arrow on top. Before you break the forces into components, you must choose your axes. It's usually best to choose an axis that points in the object's direction of motion. In this problem, the mass is moving parallel to and down the hill. So let's choose a positive x-axis that points parallel to and down the hill. Let's choose a y-axis that points perpendicular to and away from the surface of the hill. Always write down your axes. In the previous problem, we chose horizontal and vertical axes, but in this problem, we chose slanted axes. The normal force is parallel to the y-axis. The kinetic friction force is anti-parallel to the x-axis. So we can use this rule to break the normal force and the kinetic friction force into components. The normal force points in our positive y direction, so n sub y is positive. The kinetic friction force points in the negative x direction, so the x component of the kinetic friction is negative. Include a plus sign in front of the positive component because that will help you to remember to include the crucial negative sign in front of the negative component. In this problem, the weight force is neither parallel nor anti-parallel to either axis. So in this problem, we cannot use this rule to break the weight force into components. Instead, for this problem, we will need to draw a right triangle and use the SOHCAHTOA process in order to break the weight force into components. Here's the process for breaking the weight force into components. Now let's discuss this process step by step. Of course, if you thought it was easy to break the weight force into components for this problem, then you can use the table of contents in the progress bar at the bottom of the video to skip to the next topic. We need to draw a right triangle to represent the components of the weight force. We use this rule to draw the legs of the right triangle. The legs of our right triangle should be parallel to our axes. For this problem, our x-axis is parallel to the incline, and our y-axis is perpendicular to the incline. So we draw a right triangle with one leg parallel to the incline, and the other leg perpendicular to the incline. Here's a common student mistake. This would be the wrong way to draw the right triangle for the components for this problem. On the problem in the previous video, we chose horizontal and vertical axes. So on that previous problem, it was correct to draw a right triangle with horizontal and vertical legs to represent the components. But on this problem, our axes are not horizontal and vertical. On this problem, our axes are parallel to the incline and perpendicular to the incline. So for this problem, we should draw a right triangle with legs that are parallel to the incline and perpendicular to the incline. Label the sides of the right triangle. This leg is parallel to the x-axis, so this leg represents w sub x. This leg is parallel to the y-axis, so this leg represents w sub y. And the hypotenuse of the right triangle represents the overall weight force vector. Use this rule to determine the directions of the components. The head of the overall vector should overlap with the head of a component, and the tail of the overall vector should overlap with the tail of a component. Here's an example of what I mean by the head and tail of a vector arrow. Here we have the head of the overall vector. So that should overlap with the head of this component. Here we have the tail of the overall vector. That should overlap with the tail of this component, which means that this should be the head for this component. You should pause the video and memorize this rule for finding the directions of the components. The head of the overall vector should overlap with the head of a component, and the tail of the overall vector should overlap with the tail of a component. Now that we know the directions of the components, we can determine the signs of the components. W sub x points down the hill. Down the hill is our positive x direction, so W sub x is positive. W sub y points into the hill. Into the hill is our negative y direction, so W sub y should be negative. Now we're still not ready yet to apply the SOHCAHTOA equations to this right triangle because we don't know the angles inside the right triangle. we're going to apply the SOHCAHTOA equations to this right triangle. So it's not good enough to know this angle outside the right triangle. We need to know the angles inside the right triangle. Let's label these angles alpha, beta, and theta. And now let's use geometry to figure out alpha and beta. First, we need to extend this vertical line downward and extend this horizontal line leftward. That creates a new right triangle, the large right triangle ADE. We will use this rule. The acute angles in a right triangle add to 90 degrees. Focus your attention now on the large right triangle ADE, which I've highlighted in color. The acute angles in this large right triangle are theta and alpha. Based on this rule, we know that theta plus alpha is 90 degrees. We know that theta equals 40 degrees, so we can figure out that alpha equals 50 degrees. Build that new information into your sketch. Now let's shift our attention to this small right triangle, which I've highlighted in color, right triangle ABC. The acute angles in this small right triangle are alpha and beta. Based on this rule, we know that alpha plus beta is 90 degrees. We've figured out that alpha is 50 degrees, so now we can figure out that beta is 40 degrees, and we should build that new information into our sketch. You should memorize this helpful geometry fact. The acute angles in a right triangle add to 90 degrees. Now that we know the angles inside triangle ABC, we're now ready to apply the SOHCAHTOA equations to that triangle to figure out the magnitudes of the components. I've labeled this 40-degree angle at the bottom of this small right triangle with an asterisk to indicate that I'm going to use the 40-degree angle in my SOHCAHTOA equations, instead of using the 50-degree angle at the top of the right triangle. Label the sides of the right triangle. This leg is labeled as adjacent because it is adjacent to the 40-degree angle that we've chosen to focus on. This leg is labeled as opposite because it's opposite to the 40-degree angle that we're focusing on. And this side is labeled as the hypotenuse because it's across from the 90-degree angle. We can see that the length of the opposite leg represents the magnitude of W sub x. The length of the adjacent leg represents the magnitude of W sub y. And the length of the hypotenuse represents the magnitude of the overall weight vector, which we calculated earlier is 98 newtons. We use absolute value symbols in our SOHCAHTOA equations because the SOHCAHTOA equations can only tell us the magnitudes of the components. It's our job to add the plus or minus signs to the components in a separate step. We already decided earlier that W sub x is pointing in the positive x direction, and W sub y is pointing in the negative y direction. So W sub x is positive and W sub y is negative. It is crucial to include this negative sign in front of W sub y. If we leave out the negative sign for W sub y, we're going to get the problem wrong. So remember that I recommend that you should include a plus sign in front of positive components, like W sub x, because that will help you to notice when you need a negative sign in front of negative components, like W sub y. Inclined plane problems are common on exams, so you should make sure that you are comfortable with this method for breaking the weight force into components for an inclined plane problem. For this problem, we used sine for the x component and cosine for the y component. But in the problem from the previous video, we used sine for the y component and cosine for the x component. So the moral is, don't assume that you will use sine for x and cosine for y on other problems. Use the SOHCAHTOA process that we've illustrated here to determine the correct approach for each individual problem. So now we can substitute our results for W sub x and W sub y into our force table. Now the force table is complete, and next we work on the Newton's second law equations. On the left sides of the Newton's second law equations, we add the individual force components taken from the second and third rows of our force table. If an object is motionless in a component, then that component of its acceleration is 0. The object is moving parallel to the hill in the x component. The object has no motion perpendicular to the hill. The object has no motion in the y component. So we can substitute 0 for a sub y in our Newton's second law y equation. There's no reason to substitute 0 for a sub x. In fact, a sub x is what we need to determine in order to answer the question. So we will continue to use the symbol a sub x in our Newton's second law x equation. The Newton's second law x equation at this point has two unknowns. So we postpone working further with this equation. On the other hand, at this point, the Newton's second law y equation has only one unknown. So we're ready to solve this equation for n. And our result is that n equals 75.1 newtons. Now, we substitute our result for n into the Newton's second law x equation. Now, the Newton's second law x equation contains only one unknown. So now we're ready to solve this equation for a sub x. Our result is that a sub x equals 4.047 meters per second squared. I encourage you to arrange your algebra in two adjacent columns. As I've illustrated here on the screen, this two-column approach will help you to keep your algebra organized. Now we're ready to answer the question. The question was asking for the acceleration of the mass. Since acceleration is a vector, I'm going to choose to interpret this question as asking for the direction and magnitude of the overall acceleration vector. A sub y is 0, so the overall acceleration has the same magnitude and direction as a sub x. A sub x is positive. Our positive x direction is parallel to and down the hill. So the acceleration vector points parallel to and down the hill, as I've drawn here. The magnitude of our result for a sub x is 4.047 meters per second squared, which I'll round off to 2 digits in my final answer. Check that your results make sense. Little n, written without an arrow on top, stands for the magnitude of the normal force. Magnitudes can never be negative, so it does make sense that this result came out to be positive. Does the number 75.1 make sense? In this version of the free body diagram, I've represented the weight force by its components, W sub x and W sub y. Earlier, we figured out that W sub x points down the hill, and W sub y points into the hill. So in this version of the free body diagram, I've drawn W sub x pointing down the hill, and W sub y pointing into the hill. Well, W sub y is trying to begin the mass moving into the surface of the hill. To prevent that, the normal force has to cancel W sub y. So yes, it does make sense that the magnitude of the normal force has to equal the magnitude of W sub y. In this version of the free body diagram, I've drawn the arrow for the normal force equal in length to the arrow for W sub y, to reflect the relationship between those two forces. Does this result make sense? Does it make sense that a sub x came out to be positive? This means that a sub x is pointing in our positive x direction, which is parallel to and down the hill. Why does that make sense? Well, a sub x will depend on the forces in the x component. The forces in the x component are W sub x and the kinetic friction force. We know that the magnitude of W sub x is 63 newtons, and in the course of our work on the Newton's second law x equation, we happened to figure out the magnitude of the kinetic friction force. This number, 22.53 newtons, represents the magnitude of the kinetic friction force. I should be careful to include units when I write this number by itself. Well, the kinetic friction force is pointing up the hill. W sub x is pulling down the hill. We can see that W sub x has a greater magnitude than the kinetic friction, so W sub x is going to win the tug-of-war, and therefore the net force for the x component is going to point down the hill. And therefore it does make sense that a sub x points parallel to and down the hill. In this version of the free body diagram, I drew the arrow for Wx longer than the arrow for the kinetic friction force to reflect that relationship between those two forces. The direction of the velocity vector indicates the object's direction of motion. On this problem, the velocity vector is pointing parallel to and down the hill, because the mass is moving parallel to and down the hill. We found that the acceleration vector is also pointing down the hill. That means that on this problem, the acceleration vector is parallel to the velocity vector, which means that the object is speeding up. In this problem, W sub x is trying to speed up the mass. The kinetic friction is trying to slow down the mass. The magnitude of W sub x exceeds the magnitude of the kinetic friction, so the mass will speed up. What about the magnitude of A sub x? Does this magnitude make sense? What do you think? Well, here's a good way to think about that. On this problem, it's interesting to compare our result for the magnitude of the acceleration with 9.8 meters per second squared, the magnitude of free fall acceleration. Does it make sense that the magnitude of our result for A sub x is less than 9.8 meters per second squared? Well, 9.8 meters per second squared is what the magnitude of the acceleration would be if the acceleration were caused by the full force of the weight, unimpeded by any other forces. That's what free fall means. But in this problem, the box's acceleration is caused by only one component of the weight, W sub x, not by the full force of the weight. And furthermore, W sub x will be partially canceled by the kinetic friction force. So yes, for both of those reasons, it does make sense that our result for the magnitude of A sub x is less than the magnitude of free fall acceleration. Now let's do a recap of our work on this problem. The purpose of this problem is to introduce the basic method for solving inclined plane problems. This problem demonstrated that inclined plane problems can be solved using the same Newton's second law problem-solving framework that we already learned about while we were solving the problem in the previous video. The main difference between the inclined plane problem in this video and the problem from the previous video was our axes. For an inclined plane problem, rather than choosing horizontal and vertical axes, we choose slanted axes, with our x-axis parallel to the incline and our y-axis perpendicular to the incline. Make sure you write down your axes. The axes that we chose were crucial for breaking the forces into components, and also for determining that A sub y equals 0. The object is motionless in the y component, so we could substitute 0 for A sub y. In order to break the weight force into components based on these axes, we had to draw a right triangle. When drawing the right triangle for this problem, do not draw a right triangle with horizontal and vertical legs. Instead, be sure to draw the legs of your right triangle parallel to your axes. On this problem, our axes are parallel to the incline and perpendicular to the incline. So for this problem, we need to draw a right triangle with legs that are parallel to the incline and perpendicular to the incline. Remember that this is the rule that we used to determine the directions of the components. The head of the overall vector should overlap with the head of a component, and the tail of the overall vector should overlap with the tail of a component. Then we had to use geometry to determine the angles inside this small right triangle. We used the helpful geometry fact that the acute angles in a right triangle add to 90 degrees. And then we could use the SOHCAHTOA equations to determine the magnitudes of the components. And it was crucial to notice that we needed a negative sign for W sub y. Inclined plane problems are common on exams, so you should make sure that you are comfortable with this method for breaking the weight force into components for an inclined plane problem. And again, we saw that it was helpful to arrange our work on the two equations in side-by-side adjacent columns. That helps us to keep the algebra organized. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.